Imagine, for just a second, that you spend hundreds of hours meticulously building this gorgeous little ship in a bottle.
Oh, right. The classic ship in a bottle.
Exactly. It's pristine, it's perfectly balanced, and it just lives in this completely controlled, safe little environment on your shelf.
No variables at all.
Right, none. It is a closed system. But then, imagine you take that glass bottle, you just smash it on the ground, and you toss your delicate ship straight into the middle of a hurricane in the actual ocean.
Yeah, that is quite the transition.
Right. You're going from absolute sterile control to absolute unpredictable chaos. And that leap is exactly what we are examining today in this deep dive.
We are getting into the really high-fidelity world of giant-scale remote control flight simulation.
Specifically, we're looking at an environment called VSKYLABS RC-Elements Vol 1.
Which, is often abbreviated simply as RCE. And we should probably establish a clear baseline here right off the bat.
Yeah, let's do that.
When we talk about VSKYLABS RC-Elements, we are not talking about some casual digital toy. The sources explicitly define this as, quote, training-grade fidelity.
Meaning it's not an arcade game.
Exactly. It operates as a platform utilized for professional, experimental, and educational aerospace simulation.
I do want to address something really quickly for you listening, though. You might have tuned in today hoping we were going to get hyper-granular on just one plane.
Right, like flipping straight to the pilot notes for the B2X Vulcan.
Exactly, the B2X Vulcan. We actually really wanted to do exactly that, look at its specific energy management and turbine details. But when we dug into the sources provided, we realized they gave us something much broader.
Yeah, a lot broader. Instead of a narrow look at the Vulcan, the sources actually laid out this zoomed-out blueprint for the entire ecosystem.
The wild digital ecosystem that the Vulcan, along with like 24 other aircraft, actually lives inside.
Okay, so let's unpack this a bit. Because to understand the planes themselves, we first have to really understand the digital sandbox they are flying in. RCE does not operate as a standalone product. You don't just, click an app on your desktop and start flying around.
It's built inside something else, right?
Yeah, it is built entirely inside Laminar Research's X-Plane 12 engine, widely considered the world's most advanced consumer-available flight simulator engine.
Yeah, and that underlying foundation is really the only reason any of this works. By operating within X-Plane 12, RCE inherits professional-grade fluid dynamics and physics.
Wow.
It doesn't just, animate a plane moving through the sky. It calculates exactly how the air is flowing over every single surface of that airframe in real time.
So it's constantly doing the math.
Exactly doing the math. When we talk about giant-scale RC aircraft, we're talking about complex physical objects. They have real mass, real inertia, and they behave according to strict laws of aerodynamics. Well, what's fascinating here is the absolute necessity of that physical fidelity. I mean, if you want the simulation to actually be useful, you have to do it. You see, in the real world, scaling down an aircraft changes its aerodynamic properties drastically.
Wait, how so? I mean, a wing is a wing, right? If you shrink it by 50%, doesn't it just fly like a 50% smaller wing?
You'd think so, but no. The physics of the atmosphere don't scale down with the plane.
Oh, interesting.
Yeah, this involves something called the Reynolds number, which relates to fluid dynamics. To keep it simple, to a tiny, scaled-down airplane, the air it's flying through effectively feels thicker.
Thicker?
Yeah, like it's more viscous than it feels to a full-size 747. The air just behaves differently over the miniature wing. So, you can't just take the math for a big plane and divide it by 10.
Wow. Okay, so the air feels almost like syrup to a smaller model.
Relatively speaking, yeah, exactly. So by building RC elements inside that specific engine, VSKYLABS basically forces the simulation to compute real atmospheric physics.
And what's fascinating here is how that mathematical environment actually translates to the pilot. Sitting at your desk, you are suddenly forced to deal with realistic winds, turbulence, thermals.
You're fighting the weather.
Exactly. Gusts, precipitation, all these complex real-world weather conditions.
Okay, here's where I have to play devil's advocate for a second.
Go for it.
If I am stepping into a multi-million-dollar professional airline simulator to learn how to fly, like a Boeing 737, I absolutely understand why I need weather simulation.
Sure, an airliner flies through the troposphere, dealing with jet streams and massive storm fronts.
Right. But why does an RC pilot need real-world weather like thermals and precipitation?
Yeah.
I mean, isn't giant-scale RC flying mostly done at local airfields on sunny, calm days?
Well, you are assuming the air is calm just because the sun is out.
Oh, interesting.
Yeah, these giant-scale models are incredibly susceptible to what we call micro-weather. when you are flying a massive RC aircraft.
And these things are huge, right?
Oh yeah, these models can have wingspans of 10 to 15 feet, but you are still dealing with an object that is incredibly light for its surface area compared to a full-scale aircraft.
Ah, I see where you're going with this.
So to a massive airliner, a small pocket of turbulent air is just a minor bump. To a 50-pound RC model, that same pocket of air acts like a physical brick wall.
Wow. So even on a sunny day, the air is fighting you.
Constantly. A setter thermal, like a rising column of warm air coming off a hot asphalt runway, or an unexpected microgust rolling over a nearby tree line.
That would just violently alter the pitch and roll of the model.
Exactly. So if you only ever train in a standard RC simulator that provides perfectly still digitized air, you are just building this massive false sense of security.
You were learning how the plane flies in a vacuum.
Right, not how it actually behaves when the atmosphere pushes back.
Which brings us back to that ship in the hurricane analogy. VSKYLABS, using the X-Plane 12 atmospheric engine, forces the pilot to constantly fight the air.
It's all about muscle memory. Learning to manage a giant RC plane when a sudden crosswind hits on your final approach builds the precise reflexes you need.
The reflexes that save the physical aircraft from a catastrophic crash in real life.
Precisely. But, calculating those complex crosswinds is really only half the equation here.
Because the air doesn't mean anything without an airframe to push against.
Exactly. And the way X-Plane computes wind hitting an aircraft changes entirely based on the geometry of what you are actually flying.
So let's look at the actual hardware. What exactly are we trying to keep in the air in these virtual storms?
The fleet in RC Evo 1 is honestly extensive. The simulation includes 24 highly engineered, giant-scale RC aircraft.
It's a huge variety, too.
Yeah, the diversity covers jets, helicopters, VTOLs.
Which stands for vertical takeoff and landing aircraft, right?
Right, alongside aviation legends and some truly bizarre experimental platforms.
We mentioned the B-2X Vulcan earlier, which has that massive, iconic delta wing. But you also have the SR-71X Blackbird, the A-10X Warthog.
And then things like the XF-5UX Flying Pancake.
Yes, the flying pancake. For anyone unfamiliar, it's basically a massive flying disc.
It looks exactly like it sounds.
Right. And simulating how a flat disc glides through turbulent air requires an entirely different set of aerodynamic calculations than simulating the long, swept wings of the Blackbird.
Totally. The physics engine has to evaluate the lift and drag across the surface area of that disk in real time.
It has to account for how the air spills over the curved edges versus how it channels smoothly over a traditional wing.
But the geometry of the planes is really just the starting point here. The simulation engineering goes much, much deeper into how these aircraft are powered.
And here's where it gets really interesting to me. Because the sources note that the simulation covers a massive variety of propulsion.
We are talking electric propulsion, glow engines, radial engines, jet turbines,
turboshaft systems, and even rocket propulsion. Now, simulating an electric motor, turning a propeller makes sense to me.
Sure.
But simulating turbofshafts and rocket propulsion for RC planes, how does that actually change the experience for you sitting at your computer? I mean, isn't thrust basically just thrust?
Oh, not at all. Thrust is delivered in fundamentally different ways depending on the mechanical source.
Okay, explain that.
Well, it goes right to the heart of flight dynamics and energy management. You really have to think about the physical reality of these different power plants.
So take an electric motor, for example.
Right. An electric motor gives you a perfectly linear torque curve. You get instant 100% power the millisecond you push the throttle on your controller.
The response is immediate.
Exactly. A jet turbine, on the other hand, operates on a completely different mechanical timeline.
Wait, so if I'm flying a digital turbine jet in the sim, the software is actually calculating the milliseconds it takes for the virtual air to compress and ignite.
Yes. It's not just a delayed animation on the screen. The digital model in RC-Elements is engineered to react perfectly to that specific mechanical lag.
That is insane.
It has real spool-up time. So if you are flying a giant-scale RC jet turbine model and you get into trouble close to the ground...
You cannot just jam the throttle forward and expect an instant burst of speed to escape.
Nope. You'll just crash. The turbine has to ingest the air, compress it, inject the fuel, and ignite it before the thrust actually ramps up.
So if you manage your energy poorly and get too slow on your approach,
that spool-up lag will put your plane into the dirt before the engine ever reaches full power.
Wow, that dramatically alters how you fly. You have to anticipate your maneuvers seconds in advance.
You really do.
And what about a glow engine? That's the small internal combustion setup where there's no spark plug, just a constantly heated element, right?
Yeah, exactly.
Does the simulation account for the specific vibration and power band of that tiny physical piston?
It absolutely has to.
Right.
Because a glow engine uses a completely different combustion process than a turbine or an electric motor.
It's a whole different beast.
It has a specific power band where it is most efficient, and it actually creates torque-induced yaw.
Meaning the physical twisting force of the engine actually tries to pull the nose of the plane to one side.
Yep. The engine's rotation physically twists the airframe, and then, a digital rocket introduces an entirely different challenge altogether.
Oh man, the rockets.
With solid fuel rockets, you have this massive burst of acceleration, but you also have a rapidly shifting center of gravity.
Because the fuel's burning up.
Exactly. As the solid fuel burns off in seconds, the physical weight of the rocket changes drastically, which alters the balance of the aircraft mid-flight.
So the software isn't just saying, hey, the plane goes fast now. It is mathematically simulating the shifting weight of burning fuel.
And the twisting torque of a piston.
And the atmospheric lag of compressing air in a turbine, you're forced to use entirely different piloting techniques and energy management strategies just to keep these things in the sky.
That is the mechanical definition of high fidelity. But here's the kicker.
Okay.
Perfecting your energy management with a hyper-accurate engine in turbulent weather only prepares you for a flight where everything works perfectly.
Which, let's be honest, never happens.
Right. In the real world of giant-scale RC flying, things vibrate, linkages come loose, batteries drop voltage unexpectedly. Real-world flying rarely goes perfectly.
Which brings us to how the simulator prepares a pilot for the absolute worst-case scenario. RC-Elements introduces something they call test pilot mode.
This is where things get really intense.
Yeah, this mode is designed to inject progressive, random failures and abnormal situations directly into your simulation.
It is essentially a digital gremlin hiding inside your remote control.
Just waiting for the most stressful possible moment to pull a wire or break a gear.
Pretty much. The sources detail that this mode includes propulsion issues, control and system malfunctions, landing gear problem.
Overstress and overspeed events, right?
Yeah.
And specialized emergency handling.
Yeah.
But I have to ask, if I am flying my digital SR-71X Blackbird and suddenly my left elevator servo just dies, I'm gonna crash.
Probably.
So what is the educational value of punishing the pilot with random mechanical failures? Is the software just trying to bully you?
It feels like bullying, but if we connect this to the bigger picture, this test pilot mode is the true core of the training environment.
How so?
By simulating these random system failures, the software is training your reflexes and critical thinking under severe duress. Let's look at a control malfunction.
Okay, paint a picture for us.
If an aileron fails, and those are the control surfaces on the trailing edge of the wings that manage your roll, you have to instantly figure out how to keep the plane level.
Using only your tail rudder and elevator to compensate.
Exactly. You are forced to perform interactive crisis management. The simulation takes away your primary tool and demands you solve the aerodynamic puzzle before you hit the ground.
You have to figure it out in seconds. And let's talk about the overstress and overspeed events, too.
Oh, those are brutal. In a standard video game, you can pull a 20G turn at 200 miles per hour, and the digital plane magically holds together.
Right, it just bounces off the invisible ceiling.
But a physical giant-scale RC plane is a complex structure made of balsa wood, carbon fiber, fiberglass, and epoxy.
It has physical limits.
Yeah.
If you pull back on the stick too hard while going too fast, the physical airframe simply cannot handle the aerodynamic load.
You will literally rip the wings off the fuselage midair.
And the simulation forces you to respect those structural limits.
Yes. By suddenly throwing an overspeed failure at you, it bridges the gap between casually flying a digital model and the heart-pounding stress of trying to keep a 50-pound physical model in the air when an engine unexpectedly quits.
It really forces you to learn how to execute a dead stick landing.
Which is terrifying.
Yeah, a dead stick landing being the scenario where you have zero engine power and you have to rely purely on your momentum and altitude.
To basically glide a very heavy, unpowered brick safely down to a tiny runway.
It removes the safety net entirely. You only get one attempt at a dead stick landing.
You cannot throttle up and try again if you miss the approach. You're either on the runway or in the trees.
Right. So let's calculate the logistics of this whole setup. You have $129 for Vol-1 plus the cost of the base X-Plane 12 software.
Plus a specialized 8-channel USB controller.
We are talking about a significant financial and technical barrier to entry here,
It's definitely an investment.
which raises a very practical question. Is this software ecosystem purely designed for hardcore aerospace engineers doing commercial development, or is there actual tangible value here for a dedicated RC hobbyist?
Well, we really have to synthesize that cost against real-world application. The hobby of giant-scale RC flying is inherently expensive and high risk.
These aren't cheap foam toys you get at the big box store.
No, the physical models cost thousands of dollars. They require hundreds of hours to build, glue, wire, tune, and maintain.
And a single mistake, a single unexpected gust of wind, or a single servo failing at the wrong moment
Turns a $5,000 piece of flying art into a pile of splinters in 3 seconds.
The financial loss is devastating, but honestly, the psychological blow of watching hundreds of hours of craftsmanship shatter on the runway is just as bad.
Exactly. So you have to view the VSKYLABS RC-Elements environment as a highly interactive insurance policy.
Oh, that makes a lot of sense.
Think about that test pilot mode again. Let's say you are learning to fly the digital B2X Vulcan, and you push it into a severe overspeed event.
Okay.
You snap a wing spar, the plane enters an unrecoverable spin, and you crater it into the virtual runway. What did that mistake cost you?
Absolutely nothing but a bruised ego.
Right. It costs you nothing financially, but the educational yield is massive. You learned the absolute structural limit of that specific airframe.
You learned exactly how it behaves when it stalls.
You learned what the jet turbine spool-up lag feels like when you are trying to recover 3 feet off the deck.
And learning those lessons in the digital sandbox is essentially free once you were set up with the hardware.
Whereas learning those exact same lessons at the actual airfield costs you thousands of dollars and months of repair time.
That frames the value proposition perfectly. The software is not just a simulator, it is a proving ground.
Exactly. It allows you to crash 100 times over, refining your energy management and crisis response until the reactions become pure instinct.
So to wrap this all up, what we have uncovered today is that the VSKYLABS RC-Elements Volvision 1 environment is fundamentally different from a standard flight sim.
It really is.
It takes 24 diverse, giant-scale aircraft from the swept wings of the Vulcan to the bizarre aerodynamics of the Flying Pancake and subjects them to the unforgiving fluid dynamics of X-Plane 12.
It strips away the false sense of security that traditional simulators build, forcing pilots to manage true microweather.
And hyper-accurate engine dynamics, from the lag of a turboshaft to the shifting weight of a solid fuel rocket.
And of course, those random, structurally accurate mechanical failures.
It is entirely designed to prepare the pilot for the chaos of the real world. And that actually brings us to a final thought to leave you with.
Something for you to mull over long after the steep dive ends.
Yeah. We began by discussing the leap from the sterile control of a ship in a bottle to the unpredictable chaos of a hurricane.
But as digital aerospace simulators like VSKYLABS continue to advance, as they perfectly replicate the volatile microweather, the microscopic mechanical failures,
The specific vibrations of a glow engine, the exact aerodynamic stress limits of balsa wood and carbon fiber.
we have to ask a deeper question here. At what point does mastering the digital simulation require the exact same level of skill, instinct, and nerve as flying the physical aircraft?
If the virtual storm punishes your mistakes with the exact same physics as the real world, does the line between a virtual pilot and a real pilot even exist anymore?
It really blurs the line, doesn't it?
It is a phenomenal question to ponder. Thank you for coming along on this deep dive with us today.
We hope this exploration gave you a completely new perspective on the complex physics and high-stakes engineering operating behind the scenes of digital aerospace.
Keep asking questions, keep looking for those moments of discovery, and we will catch you on the next one.